The curves in this figure show that the smaller the damping, the taller and narrower is the resonance peak. If we go on changing the driving frequency, the amplitude tends to infinity when it equals the natural frequency, but this is the ideal case of the zero damping, a case which never arises in a real system. And the damping is never perfectly zero. Is never perfectly zero. Now, the second case is the driving force, driving frequency close to natural frequency, as shown in figure B2, a system of 5 sample pendulums suspended from a common rope. If omega d is very close to omega, then m omega square means omega d square would be much less than omega dB. For any reasonable value of b, then it reduces to a barabar f naught bata w dB. This makes it clear that the maximum possible amplitude for a given driving frequency is governed by the driving frequency and the damping and is never infinite. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance. To illustrate the phenomenon, we consider a set of 5 sample pendulum of assorted length suspended from a common rope. The pendulums 1 and 4 have the same length and the others have different length. Now let us set pendulum 1 into motion. The energy from this pendulum gets transferred to other pendulums through the connecting rope and they start oscillating. The driving force is provided through the connecting rope. The frequency of this force is the frequency with which pendulum 1 oscillates. If we observe the response of pendulum 2, 3 and 5, they first start oscillating with their natural frequency of oscillation and different amplitudes. But this motion is gradually damped and not sustained. Their frequencies of oscillation gradually change and ultimately they oscillate with the frequency of pendulum. It means the frequency of the driving force, but with different amplitudes. They oscillate with a small amplitudes. The response of pendulum 4 is in contrast to this set of pendulums. It oscillates with the same frequency to this set of pendulums. It oscillates with the same frequency as that of the pendulum and its amplitude gradually picks up and becomes very large. A resonance-like response is seen. All mechanical structures have one or more natural frequency, and if a structure is subjected to a strong external periodic driving force that matches one of the